Alright guys, so you can see in your unit packet, I think starting on page 11, there are several practice problems available for you to get more support on these new ideas. One that I thought was a little more interesting than the others was number 4, so I'm going to model that one. And again, these videos from here on out are optional. If you're ready to dive into your problem set, please feel free to do so. But for folks who are just craving a little bit more modeling, I'm going to go through a handful more in the next set of videos. So here on number 4, we have our function, and it's expressed to us generically with a random constant there called c showing up in our numerator and our denominator. And we want to try to find the equation of the tangent line when x equals 0. So just like the last problem, I'm anchoring myself in this template, and I know that I've got 0 for my x value. Additionally, to find the y value, remember that always is just going to entail subbing into your original function for x. When I find f of 0, I get c squared minus 0 squared over c plus 0, which reduces to c squared over c, which I can go even further with and get a value of c. Sorry, that was a little yucky. That's a c. Okay. To find my slope, as we just saw, I need to find the derivative at 0. I'm just going to go through the motions in a way that I think maybe you might when you see this problem, and then I'll show you a trick at the end. If I'm not thinking too much about this, I'll notice there's a quotient, and I'll just start finding derivatives. So the low function is c plus x, and I need to find the derivative of the high function. Be careful here. You have to ground yourself in the idea that c is just a constant. Derivatives of constants are 0. So even if I have c squared, like I see up here in the numerator, that is still just a constant. I'm squaring that constant, I'm still getting a number out of there, and the derivative of a number is 0. So the derivative of the top is simply negative 2x. Minus high, c squared minus x squared, d low, the c goes away, and the derivative of x is 1. All over c plus x squared. Doing some simplification here, I get negative 2cx minus 2x squared. That came from some distribution. Minus more distribution over here, a c squared plus an x squared, all over c plus x squared. I can keep going here. My numerator becomes negative 2cx minus x squared minus c squared over c plus x squared. I'm going to just go ahead though and plug in, and I probably could have done this earlier. Remember, I want the derivative at 0. So I need to be really aware that every x is going to be replaced with a 0. And I'm noticing that I made a minor mistake here. That squared needs to go on the outside. My bad. Like it did up above. So everywhere there's an x, I sub in 0. That's negative 2c times 0 minus 0 squared minus c squared, all over c plus 0 squared. Simplifying that, I have 0 minus 0 minus c squared over c squared. Going further, negative c squared over c squared. Voila, my slope is negative 1. So I'm just going to real quick take that and go over here. There's the equation of my tangent line. Something you might have noticed that I definitely want to point out, this original function, c squared minus x squared over c plus x. If you listen really carefully, you can probably hear that function telling us, factor me, factor me, factor me. In particular, the numerator is just c minus x over times c plus x. I've got the c plus x down low. Those things are gone. Simplified function then is just c minus x, which means the derivative in a much more straightforward manner is negative 1. please have your algebra radar on when you're doing these. A lot of times the algebraic manipulation, I said this earlier, is way simpler than the quotient rule or the product rule.